In this video, we're going to be looking at how do you integrate using the natural logarithm, or in this case, ln. And ln is a very nice way to integrate. If I have some sort of integral equation, where I want to integrate the derivative of a function on the numerator divided by the original function, the answer to this is simply the ln, the natural logarithm, of the absolute value of the original function plus the constant of integration, plus c. So you can see it's a fairly basic equation. Now we just have to practice this rule again and again till we get much better at it. So let's have a look at our first example. Let's suppose I wanted to integrate 2 divided by x plus 3. We'll make it easy for the first one. Let's say we want to do 1 over x plus 3. Well, is the derivative of the denominator on the numerator? Well, in this case, yes it is. We can see the derivative of x plus 3 is simply using the power rule 1. And that's exactly what we have on the numerator. So if you wanted to integrate this, we can simply say it is the natural logarithm of the absolute value of x plus 3 plus c. And let's carry on now. We can say another example is the integral of 2 over x take 1 plus 3 over x plus 2. This one looks a bit harder, but it's still the same logic. All I'm going to do is I'm going to split this integral into 2 separate ones. So I'm going to say it's the integral of 2 divided by x take 1 plus the integral of 3 divided by x plus 2. As you can see, we kind of have the derivative on the denominator on the numerator. Almost, not quite. If we have the derivative of x take 1, that's simply equal to 1. And on the numerator, we have a 2. That's a bit tricky. Not really. All we do is we can factorize out a 2 from here. So this is the same as 2 times 1. And we can bring, a property of integrals is we can bring any scalar multiple inside the integral to the outside. So we are allowed to bring scalar multiples to the outside of the integral. And there we have it. We have the derivative of the denominator on the numerator. And I'm simply going to do the same logic with this one here. All I'm going to do is I'm going to factorize out a 3 on the numerator to get 3 times 1. And you're allowed to bring scalar multiples to the outside. So this is the same thing as 3 times the integral of 1 over x plus 2. And this will yield you with 2 times. Okay, because we have f dash x, we have the derivative on the numerator and the original function on the bottom. This is 2 times the natural logarithm of x take 1 plus 3 times the natural logarithm of x plus 2. And obviously, plus the constant of integration. That is how you integrate this question here. In a previous video of mine, you would have remembered that we did integration by partial fractions. That is literally what the integration of partial fractions is. We are just integrating using the natural logarithms by simply splitting it into partial fractions first. And if you want to have a look at that video, I'll put it in a little pop-up or it's in the video description as well. And you can also just go to my YouTube channel, youtube.com/sirexplains, and you can see the video that's over there. So let's carry on. Now we want to integrate a different ln value. We want to integrate 5 divided by 2x take 3. And to integrate this, we need the same logic. We need the derivative of the denominator on the numerator. So if we want that, currently we have the derivative of the denominator, derivative of 2x take 3 is simply equal to 2. But on the top of this fraction, we have a 5. So all I'm going to do is I'm going to bring this 5 out the front, and we're left with 1 on the inside. Still doesn't help us, so I'm going to times the inside of this integral by 2. hold on a minute, I can't just change this to a 2. I can't just times something by 2 just because I felt like it. So if the opposite of timesing by 2, the opposite of this is timesing by a half. So if on the inside I times by 2, on the outside of the integral I must times by a half. Another way of saying times by half is simply divide by 2. So there we go. If I wanted to integrate this now, the derivative on the denominator is now on the numerator. So all I can say is 5 divided by 2 times the natural logarithm of 2x take 3 plus the constant of integration. That's how you integrate this question here. Next problem, I'm going to give you some time for this question here. The integral of 2x take 3 divided by x squared take 3x plus 1. Pause the video and have the go at this. Okay, so now what we can see here is the derivative of the denominator is on the numerator. So if we differentiate x squared take 3x plus 1, we can see that that's the same thing as 2x take 3. And we have this on the numerator right over here. So all we have to do now is this is the same thing as the natural logarithm of x squared take 3x plus 1 plus c. We'll do one last example. Integral of 8x plus 4 divided by 2x squared plus 2x plus 1 dx. Pause the video and have a go at this question here. Well, what is the derivative of the denominator? The derivative of 2x squared plus 2x plus 1 is simply equal to, bring the power to the front, 4 times by x, take 1 from the power, is just x to the power of 1, or just 4x, plus 2. That is our derivative. Do we have that on the numerator? No, we don't, but we can get it if we want to. In this case, I can write this as the integral of 2 times 4x plus 2. Now hold on a minute, that was our derivative. 4x plus 2 was literally our derivative of the denominator. So all I can say now is I can factorize out the 2, i.e. bring this 2 outside the front, because it is just a scalar multiple at the end of the day, and that is a property of integrals. And all I can say now is this is the same thing. I'm just going to give myself some more space. I can say that this here is the same thing as 2 times the natural logarithm of absolute value of 2x squared plus 2x plus 1 and plus the constant integration. Is this my final answer? No, it is not. Notice how I've always put the absolute value for every single one of these equations, for every single one of these integrals. Well, I tricked you. In this one, you do not need an absolute value. In fact, some courses you might even get docked marks. And the reason for that is this function here, this 2x squared plus 2x plus 1, is always going to be more than 0. If I were to sketch out a little graph of this quadratic, we can see that, first off, the discriminant of this function, the discriminant, is b squared minus 4ac, where in this case the value of a is 2, the value of b is 2, and the value of c is 1. So if I were to work out the discriminant, this would be 2 squared, 4, minus 4 times 2 times 1. And that gives me 4 minus 8, which is equal to minus 4. And those of you that remember discriminants, if the value of your discriminant is less than 0, that means the quadratic has 0 solutions. Another way of saying solution is root or x-intercept. There are 0 x-intercepts, 0 roots, 0 solutions. And the only way that your quadratic can look in this case is it can either be concave up like this, or it can be concave down like this, having no x-intercepts. Well, in this case, we know because the value of a is greater than 0, it must be a concave up quadratic. So in this case, we can reject this graph. So we can say simply, this is our quadratic. And if you notice our quadratic, there's no need for an absolute value. The reason we don't need an absolute value is because this function is always more than 0. So there's no absolute value to correct. It's not like this quadratic is going to equal to -5 ever, hence we need the absolute value to make it equal to +5. We never need this. The quadratic will always be positive. So including the absolute value might actually screw you over.